For this section, we're going to be talking about graphing the functions sine and cosine. We'll be talking about how to graph them in their basic forms, meaning their parent functions, and then we'll talk about how to graph them in essentially their most complicated forms using transformations. So, to start off with, we say that a periodic function is one with the form f of x equals f of the quantity of x plus np for a smallest period p. So let's talk about what this is saying. So let's do a quick recall here. What's sine of pi over 2? Well, we know that sine of pi over 2 is 1. That's a unit circle value. From there, what's sine of pi over 2 plus 2 pi? Well, pi over 2 plus 2 pi just means we started at the angle pi over 2 and then we made a complete rotation. If you make a complete rotation, we know that you'll end up with the same trig function value that you started with at your original angle. So sine of pi over 2 plus 2 pi still gives us 1. And sine of pi over 2 plus 4 pi, well, that just means we've made 2 complete rotations. We're dealing with the same angle in terms of a reference angle. It's still going to be pi over 2 is our main focus. So sine of this angle is the same thing as sine of pi over 2 again, which is 1. So notice every time we travel 2 pi or a complete rotation, we repeat the values for our trig function sine. And the same thing is true for cosine. So we introduce a fact that says sine of theta is equal to sine of theta plus 2 pi n. And cosine of theta is equal to cosine of theta plus 2 pi n, such that n is in the integers. Remember, this symbol means in or within. It looks like a capital E that's kind of curved. Okay, so we're now using this periodic function notation for sine and cosine. We're saying if you take an integer, meaning a whole number that's positive or negative, and you multiply it by 2 pi and add that to your angle, it'll be the same thing as if you just took the original angle and plugged it into sine. So 2 pi represents the period of sine, and the same is all true for cosine. So with all of that in mind, we now want to sketch f of theta equals sine of theta such that theta is between negative 2 pi and 2 pi. And the way we're going to do this is we're going to use our quadrantal angles. They cover basically everything we need to know about this graph. So we have theta and sine of theta, which gives us a table that we can plug our values in. So we're going to use the quadrantal angles again. So let's just go ahead and start with 0, pi over 2, pi, 3 pi over 2, and finish up with 2 pi. 0 through 3 pi over 2 are the quadrantal angles that you would deal with on a unit circle in general. And then remember, 2 pi is just what you get when you rotate all the way back to the angle of 0. So if we plug 0 into sine, sine of 0 is 0. If we plug pi over 2 in, sine of pi over 2 is 1. Sine of pi is 0 again. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0 again. Okay, now one quick note to make here is you might be thinking, well, why isn't the period of sine just pi? Why is it 2 pi? Because we traveled from the angle of 0 to the angle of pi and we repeated a value. But it's important to note that we're not repeating all values there. We only start repeating all of our values over again after we reach 2 pi. And then everything from here on out will start repeating everything that occurred within this range or this domain. Okay, so notice we got this -1 here, but here we got a 1. So the values aren't repeating over a distance of pi, they're repeating after a distance of 2 pi. So from here, let's go ahead and plot these points. We have 0, 0, pi over 2, comma 1. We'll go ahead and call this pi over 2. And we'll call this 1. So if this is 1, we need to make a note on our graph. We have 1, 2, 3, 4, 5, 6 tick marks here. And likewise, we have 6 here, so we'll call this -6. And if this is going to be pi over 2, then that means this should be pi, 3 pi over 2, and finally 2 pi. And likewise, this would be -pi over 2, -pi, -3 pi over 2, -2 pi. So we just need to make note of the last one and the first one, the bottom one and the top one, so that we know how this graph is laid out, so anybody could read it. Okay, continuing on from here, we have the point pi, comma 0. Next we have 3 pi over 2, comma -1. And finally, 2 pi, comma 0. Now, if we were to connect these points, it would seem that it's going to look like a V, like a very straight edge, and then another very straight edge. But it's very important to note that if we were to actually fill in all of the little points in between 0 and pi over 2, and in between pi over 2 and pi, and so on, it actually creates more of a curved edge, like so. So always make sure you're not putting a V shape here. It's got to have a curve to it. And this is what the graph of sine looks like between 0 and 2 pi. But remember, we wanted the graph from -2 pi to 2 pi. So how can we get that using this? Well, remember that we said that sine is a periodic function and it repeats every distance of 2 pi that you set, which means if we were to take this point right here and move it 2 pi to the left, we would get the exact same y value. The same thing is true of this point. If we move it 2 pi to the left, so half a pi, pi, 3 pi over 2, 2 pi, it has the same y value. This point as well, we'll move 2 pi to the left. This point will do the same thing. And this point will do the same thing as well, getting us right back to where we started. And if we connect the dots with the curve, we now have the entire graph of sine of theta from -2 pi all the way to 2 pi. Really, you would want to put this all in the same color so that it's clear that this is all one graph, but I wanted to show it in 2 different colors to show that using the idea of a periodic function, we didn't have to go through and graph any new points. We could literally just shift the entire graph over and get our graph again. Okay, so continuing on from here, we can make some important notes. First of all, we say that sine, sorry, I'm getting a little bit ahead of myself. Let me start with this definition here that says an odd function is symmetric to the origin and satisfies f of -x equals -f of x. So that's saying that if you have an odd function, you can essentially take the negative value outside of the function and multiply it to the outside. So you can take it from the inside and multiply it to the outside, and you have the same result. And what this means graphically is if we take the graph and spin it upside down, it will look the same. We call this symmetric to the origin. So, looking back at this graph, if you were to rotate this graph, meaning if you were to turn your screen upside down, spin it 180 degrees, so on, you would end up getting the exact same shape that you started with. And we may be able to do this actually. If we rotate this entire thing 180 degrees, notice that the graph still starts with a y value of 0, goes to 1, back to 0, down to -1, and back up to 0, and does the same thing again. Pay attention to the shape. Up, down, up, down, up. If we rotate it back to the original, again, up, down, up, down, up. So that means sine is an odd function, which is what we have for this fact right here. And we can also show that with this problem. We want to prove that sine of negative pi over 2 is equal to negative sine of pi over 2. Well, a way that we can do that is by adding 2 pi to this negative angle inside of sine. We're just completing a whole rotation, so that won't change the trig function value of this angle. So we get sine of 3 pi over 2, and we want to check if that's equal to negative times sine of pi over 2. Well, sine of pi over 2 we know is 1. Sine of 3 pi over 2, that's one of our unit circle values, our quadrantal angles. We know that's equal to -1. And on the right side, we just have negative times 1, which is -1, which means it checks out. Okay, continuing on from here, we say that an even function is symmetric to the y-axis and satisfies f of negative x equals f of x. Meaning if you have a negative value inside of your function, it's the same thing as if you just throw the negative away entirely. When this is the case, we say that the y-axis is essentially a mirror. Whatever your graph looks like, if you fold it over on the y-axis, just as if you folded a piece of paper, everything will lay perfectly on top of the other side. The right side will lay on the left will lay on the right. And this is true for the graph of cosine. So we say the graph of cosine is an even function. Now it is worth quickly showing what the graph of cosine looks like. This will just be a very rough sketch, but it's just to give an idea of what we're dealing with. We'll show it in more detail in a little while with another example. But remember that cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is -1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is back to 1. So if we connected these dots here, we'd get something that looks almost like a cursive U or a parabola with these bent edges on the sides. Now it just looks like that because we're graphing it from 0 to 2 pi. If we were to continue on, let me make a note of this 2 pi here. If we were to continue on to the left side and we were to plot cosine of negative pi over 2, it'd give us 0 as well. And connecting the graph to that point, we get a shape that more resembles sine. If you just look at this section of the graph of cosine, notice it looks exactly like the graph of sine. Okay, so now with that brief showing of the graph of cosine, we can get into graphing sine and cosine using much more complicated functions. Okay, so to start off with, the process says to graph f of x equals a sine of bx plus c plus d, or f of x equals a cosine of bx plus c plus d, meaning to graph these using transformations. We're going to start by solving an inequality. We'll set what's inside of sine or cosine greater than or equal to 0 and less than or equal to 2 pi to find one period of the graph. Because once we have one period, we can just re-sketch it over and over and over again because it's a periodic function. From there, it's a quick note. We just need this notation to say that step 1a, the first step, gives negative c over b is less than or equal to x, which is less than or equal to 2 pi minus c all over b. And from there, the length of a period will always be p equals 2 pi over b. Okay, so steps 1a and 1c are the important ones. Step 1b is just there because we need to make a quick note of this so that step 2 makes sense. And step 2 says we need to find p over 4 and then add it to negative c over b, meaning the initial part of our period, 4 times. Once we do that, we are going to list all the vertical transformations. We'll create a table and plug the 5 values found from step 2 into sine of bx plus c. And then finally, we can graph that table and apply all of the vertical transformations. We don't need to worry about horizontal transformations because they're all taken care of with these steps of solving this inequality and finding the new period and things like that. This process seems overwhelming at first. I understand that, but as you go through it, difficult though it may be, it will make sense because it is the exact same thing over and over and over every single time. So it will become second nature. You'll be able to just do it without even thinking about it as long as you just keep practicing it a bunch. So with that, let's go ahead and try this out. We want to graph f of x equals 1 minus 2 cosine of x minus pi over 4. Okay, so to start off with, we need to set up our inequality. 0 is less than or equal to x minus pi over 4, which is less than or equal to 2 pi. And we're going to solve for x. We'll do that by adding pi over 4 to all 3 values in this inequality. And when we do this, we get pi over 4 is less than or equal to x, which is less than or equal to 2 pi plus pi over 4. I'm going to take care of the fractions really quickly here. 2 pi written with a denominator of 4 is the same thing as 8 pi over 4. Plus pi over 4 would give us 9 pi over 4. So just a quick note on that, it's just like adding 2 and 1/4. Okay, we just don't have a lot of room to write all of that out, I apologize. So from here, we now know our new period. We're not graphing from 0 to 2 pi anymore. That's for the parent function of cosine. In this case, the period is from pi over 4 to 9 pi over 4. From pi over 4 to 9 pi over 4, we'll get that U shape of cosine that we're always looking for. Okay, so from here, we need to find our period, P, which is always 2 pi over b. And b in this case is the value multiplied to our x, which is just 1. So we get 2 pi over 1, which is just 2 pi. So the period is the same as normal. We travel a distance of 2 pi, we get repeating values for cosine. If the period were pi, for instance, then that would mean every time we travel a distance of pi, we would start repeating our values. And that happens whenever you change what's being multiplied to your x. So we now need to find p over 4, which is 2 pi over 4. Simplifying this, we'll divide the top and bottom by 2. That gives us pi over 2. So we're going to add this to the starting value, pi over 4, 4 times. So we start with pi over 4. And I'm going to copy this down twice. It'll be clear in a moment why we're doing this, but you should do this as well. We have pi over 4. We're going to take pi over 4 and add pi over 2 to it. Pi over 4 plus pi over 2 is the same thing as 1/4 plus 1/2. That would give us 3/4, which gives us 3 pi over 4. So in the bottom, we're listing all the simplified values. Now we get 3 pi over 4 plus pi over 2. 3 over 4 plus 1/2 gives us 5 over 4. So 5 pi over 4. Now we take 5 pi over 4 and add pi over 2 to that. So far this is 1, 2, 3 times we've added pi over 2. We're going to need to do it one more time after this. 5 over 4 plus 1/2 gives us 7 pi over 4. And finally, 7 pi over 4 plus pi over 2 gives us 9 pi over 4. These are the 5 values we're looking for our table. If you've done this correctly, your first value and last value should always match the values and the inequality you solved. If they do not, you've made a mistake somewhere. So, we'll go ahead and create our table, we'll list our transformations, and then we'll begin graphing. So starting off with our table, we have pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and 9 pi over 4. These are our x values, and remember, we're going to be plugging them into cosine of x minus pi over 4. Now, the beautiful thing about this method is we don't actually have to plug these in. These values are the new quadrantal angles. Meaning, remember when we initially plugged these values in for cosine, we would pick 0, pi over 2, pi, 3 pi over 2, and 2 pi. What happened when we plugged 0 into cosine? We said the result was 1. What happened when we plugged pi over 2 in? We said the result was 0. When we plugged pi in, the result was -1. When we plugged 3 pi over 2 in, the result was 0. And when we plugged 2 pi in, the result was 1 again. This table, these 5 values, will always be the original quadrantal angles if you've done this correctly. So just commit to memory. Cosine will always give you 1, 0, -1, 0, 1. For sine, you'll get, if you want to make a note of this, 0, 1, 0, -1, 0. Just like we did in the previous problem. Feel free to look in your notes or rewind the video to see that table for sine. You'll always get the same quadrantal values here. So from here, we just need to list our transformations, graph it, and then apply the transformations to that. So making our list, and we're a little bit short on room here, so I'll try to fit this in. We need to note if there are any vertical transformations. So the first type of transformation we always look for is there a vertical reflection? Meaning, are we multiplying the outside of our function by a negative? And in this case, we are. We're multiplying by a -2. That negative means we have a vertical reflection. Okay, so continuing on from there, we check, are we multiplying by a number that's not just 1? And in this case, we are multiplying by a 2. That means we have a vertical stretch. Whenever you're multiplying by a negative, you get a reflection. That means the graph flips over the x-axis like a mirror. Whenever you're multiplying by a number that's greater than 1, that means that you have a vertical stretch. All of your y values get pulled apart. Whenever you're multiplying by a number between 0 and 1, your y values get smushed together like a sandwich. And finally, the last one to note is, are we adding or subtracting anything from the function? And in this case, there's a +1 on the outside. That means we're adding 1. That means the function will go up by 1. If you're not comfortable with these transformation methods, I suggest you look up one of the past videos that really goes through how to deal with these vertical transformations. But hopefully you're comfortable with what you're seeing here right now. So, with this in mind, let's go ahead and start graphing. So, we need to graph from pi/4 to 9pi/4. So we'll make a note here. We'll start at pi/4. The graph will then go to 9pi/4, and each tick mark from here will be a distance of pi/2. So we have 3pi/4, 5pi/4, 7pi/4, and finally 9pi/4. Okay, and now from here we can start plotting our points. So we have pi/4, 1. We'll put that right here. 3pi/4, 0. 5pi/4, -1. That's going to go about right here. 7pi/4, 0. And 9pi/4, 1. So we get the parent, well, not the parent function, I apologize. We get the base function that looks like this. I apologize if this looks like it has a bit of a V shape to it. It should be more curved than that. Let me redraw this. That's a bit better. Okay, now we need to apply the vertical reflection, vertical stretch, and a shift of up 1, and we're done. Everything else will be taken care of. So to start off with, the vertical reflection, we'll go ahead and take care of that in red. That means everything that is on the x-axis will stay where it is. Remember, think of the x-axis like a mirror. From here, anything above the x-axis will flip down like a mirror. and anything below the x-axis will flip up. Just like so. From here, we now take care of the vertical stretch. We're going to take every y value and pull it apart because it's being stretched. How much we pull it apart is based on what we're multiplying by, which is a 2. So all of our y values get multiplied by 2. So this -1 will become -2. We pick up at the red graph, which is where we just left off. This y value of 0 multiplied by 2 stays where it is. This y value of 1 multiplied by 2 becomes +2. This 0 multiplied by 2 is still 0, and this -1 multiplied by 2 is -2. Oh, sorry. So connecting our dots, we get the same shape, but it just looks a little bit more stretched out, hence the vertical stretch. Okay, and now finally to finish it from here, I'm going to go ahead and pick blue. We now need to apply a shift up 1. So every green value on this graph will go up 1. So this point is going to go up to where this red dot was. This green point will go up here. This point will go here. This point will go up here, hopefully as much as you can, matching it horizontally with the point that is also at y = 1. And finally, this point will go up here. Same thing, try to match it with the point over here because they are at the same height. And when you connect the dots, you end up getting this final shape in blue. This represents the graph of f of x, which we should make note of. Okay, this was a very long process. I understand it's very intimidating to look at, but remember, it will always be the same thing. Solve the inequality, find the period, divide the period by 4, add that value 4 times to your initial value in your inequality. Create a table with those values and always have the same quadrantal angles. Create a list of your vertical transformations and then graph using the vertical transformations. And I want to be very clear here. The only part of this graph that is the final graph is the one in blue. Everything else is the work to get to that graph. All right, so to finish this up from here, we have a final problem. We want to graph f of theta equals 3 sine of 2 theta minus pi, all minus 2. I know this will be intimidating, but I want you to take a moment, pause the video, try to get as far as you can through this problem on your own, and then resume the video and we'll try it together. Okay, so trying this together, first thing we have to do is solve the inequality. So we have 2 theta minus pi, we have to set that greater than or equal to 0 and less than or equal to 2 pi. We will add pi to all 3 of these values to start solving for theta, which gives us pi is greater than or equal to 2 theta. Sorry, pi is less than or equal to 2 theta, that is, which is less than or equal to 3 pi. And then dividing everything by 2, we get pi over 2 is less than or equal to theta, which is less than or equal to 3 pi over 2. This is the new period of our graph. From pi over 2 to 3 pi over 2, we get the original graph of sine. From here, we want to find p. which is 2 pi over b. And in this case, b is the value multiplied to theta, which is 2. So we get 2 pi over 2, which is just pi. So our period is no longer 2 pi, it's pi. Every time we travel a distance of pi, the values repeat themselves. We travel a new period. Okay, so continuing on from here, we need to find p over 4 and then add it to our original value, pi over 2, 4 times. So p over 4 is going to give us pi over 4. So starting at pi over 2, remember we're going to make this list twice. One for the work, one for the answer. We get pi over 2 plus pi over 4. Pi over 2 plus pi over 4, if you find a common denominator, would give you 2 pi over 4 plus pi over 4, which is 3 pi over 4. Now we take 3 pi over 4 where we just left off, and we add pi over 4 to that again. 3 pi over 4 plus pi over 4 is 4 pi over 4, which is just pi. Pi plus pi over 4 is the same thing as 4 pi over 4 plus pi over 4, which gives us 5 pi over 4. And we just have to add it one more time. 5 pi over 4 plus pi over 4 gives us 6 pi over 4, or 3 pi over 2. We'll do a quick check. Pi over 2, 3 pi over 2, those match the end values of our inequality. That means we've probably done this correct. We know for sure we haven't gotten those two wrong. Okay, so now we'll create our table with our value theta and sine of 2 theta minus pi. And we're plugging in pi over 2, 3 pi over 4, pi, 5 pi over 4, and finally 3 pi over 2. Remember, these values will always be the same, the quadrantal angles of sine, so we get 0, 1, 0, negative 1, 0. And now we can make the list for our vertical transformations and begin to graph. The first vertical transformation, we check if there's a vertical reflection. In this case, there is not. We are not multiplying by a negative to the outside of sine, but we are multiplying by a 3, which means we have a vertical stretch. The value is not between 0 and 1, it's greater than 1. That means it's a vertical stretch. Continuing from there, we check if we're adding or subtracting anything outside of the function. We're subtracting 2. That means it's going to go down 2. Okay, so we can get this graph started. We have to start at pi over 2. And now we add these 4 other marks, 3 pi over 4, pi, 5 pi over 4. Since 5 pi over 4 is going to have a negative value, I should put it up here, but just for consistency, I'm going to leave all the tick marks with their values below them so it doesn't look too difficult to read. And finally, 3 pi over 2 will go here. Okay, so we need the value 0 at pi over 2, 3 pi over 4, comma 1, pi, comma 0, 5 pi over 4, negative 1, and 3 pi over 2, 0. So our graph is going to look something like this to start off with. It's messy, it's not perfect, but it does end up giving us a very good idea of what the graph will look like at the end. So from here, we now apply our vertical stretch, meaning we multiply every y value by this 3. If it helps you, make a note of what number you're multiplying by. So we'll go ahead and put that in red, just like the previous one. So multiplying every y value by 3, 0 times 3 is still 0, 1 times 3 is 3, 0 times 3 is 0, negative 1 times 3 is negative 3, and 0 times 3 is 0 again. Connecting our dots, we get a shape like that. I swear I could draw this better on a chalkboard or something like that. But again, it's just a rough sketch. And now finally from here, we go down 2. So we'll go ahead and put that in green. Every red point will go down 2. So this is going to go down here. This point will go down to 1. This point will be horizontal to this one because they both started at 0 and now they're both at negative 2. And this point will also go down to that negative 2. And finally, this point at negative 3 will go down to negative 5. We'll also make a note that up here we went all the way up to 3. So connecting our dots, we get a final graph that looks like this. And we always want to make note what one is the final graph, so we'll call this f of theta. And this graph in green is what f of theta equals 3 sine of 2 theta minus pi all minus 2 looks like.